All right, today our objective is to create and use exponential functions that accommodate various time intervals. We've been working with exponential functions the last few days. Um, we are going to kind of see some more complex scenarios where we need to make some adjustments to what we're doing. Um, let's just dive right into example problems. After kind of this statement at the top of your note sheet. So depending on the context of the problem, the input of our exponential function will need to be modified. So that means we either need to multiply or divide or add or subtract from in order to properly model the problem. Let's take a look at example one. Chris starts a popular club at school. The club starts with only 2 members but triples in size twice per week. Write an equation representing the number of club members after t weeks. And the thing that is going to throw us off more so than previous problems is this whole statement twice per week. If I kind of go through and do that close read and kind of pick out different information, I know it has 2 members to start, so my start at 2. And I know I'm tripling in size, so I'm going to times by 3. And we're talking about t in weeks as well. However, this statement, twice per week, is going to come into play. Twice per week. So if I just go and kind of create this function, let's say members as a function of t weeks. Normally we'd set it up, we do our initial value, 2 times, it's going to triple every week, so that happens over and over and over again. However, it happens twice per week. So if I just write x up here, that doesn't exactly capture it, right? That only covers once per week. So what I need to do is multiply that input, that exponent, by 2 every single time, because every single week that goes by, it's tripled twice. So with that slight tweak to our problem, we can then appropriately model it without having to change too much, just with interpreting the context of the problem. Then if we want to find out how many club members there are after 3 weeks, all we got to do is what we've done previously. M of 3 equals 2 times 3 to the 2 times 3 power up top. And note that I'm going to throw some parentheses around this just to make sure that I'm doing my order of operations correctly, because if we think about it, it's being tripled 6 different times if it's being tripled twice per week. I'm going to go in Desmos. I'm going to calculate this. I got 2 times 3, raising it to the power of 2 times 3. Or if you wanted to, you could type in 6. It looks like I have 1,458 members after that amount of time. 1,458. So we're going to practice this with a couple other examples, and then see example 4 will be slightly different. Example 2, the value of a cell phone depreciates at a rate of 4% every month. If a new phone costs $300, write a function that represents a cell phone value after X years. So right off the bat, I can see this mismatch that we have every month, and X is in years. So I'm going to make a quick note here, 12 months per year. All right, that's just a quick kind of side note there. Oops, lost my notes, it looks like. All right, got those back. And then it looks like I also know that I start at $300, and this is a depreciation problem. It's a decay problem at 4%. So that 4% is going to convert to 0.04. And I know that base, since it's decay, is to be 1 minus 0.04, which is equal to 0.96. That'll be the base I use in my problem. So I come up with those numbers. Then I get a formula. Let's say cell phone C as a function of X, because we're talking about X years. It starts at that 300. We're going to multiply by that 0.96 over and over and over again. And then up top, it's not just to the number of years, right? Because what's actually happening is it is hitting 12 times per year. So whatever year we got to put in, we got to multiply by 12. Then once we set that up, if we're trying to find it after 5 years, we just plug that into our function that we created. Our cell phone at 5 years is equal to 300 times 0.96 to the 12 times 5. I'm going to throw some parentheses around that up top just to make sure I'm calculating it correctly. I'll go into Desmos, 300 times 0.096 to the 12 times 5. And if you're kind of doing that in your head, 12 times 5 is 60. That's the exact number of months that it's hitting. And it looks like our cell phone now is only worth $25.91 with rounding. 25.91. All right, one more example type. We have a population that triples in size every 10 years. Write an equation that represents the population size after t years. So reading through this, it looks like I start at 2,500. And I am going to be tripling, so I know that's going to be times 3 over and over and over again. However, it's every 10 years. And we're going to model this with t years. So this is a little more tricky. If I write my equation now, let's say population after t years, I'm starting with that 2,500. I'm multiplying by 3 over and over and over again. And I'm raising it to the t power, something with the t power. However, it's not going to be 10 times t, right? Because if we pass a year, it's not like we've tripled our population 10 times. Instead, we got to spread that tripling out over the 10 years. So we're actually going to divide by t up top. We'll have t divided by 10. Because if I want to find that first tripling section, if I plugged in 10 divided by 10 would give me 1. We would only triple the 1 time. So if I'm plugging this in to kind of calculate out what happens at 40 years, my population at 40 equals 2,500 times 3 to the 40 divided by 10. And I'm going to throw that in parentheses up top. And I'm going to let Desmos do that math there, though. And you can see that we're probably going to triple. We should triple 4 different times because 40 divided by 10 would give us 4. I plug that in, 2,500 times 3 to the 40 divided by 10. And that gives me 20250. And let's just kind of explore that other idea, 2,500 times 3. If I just raise it to the 4th power, okay, that gives me the same thing, right? It's taken 4 segments of 10 different years. So that means it's tripled 4 different times. This 202,500 is our population, 202,500. All right, last problem. So an artist makes a design using rows of tiles. The first row has 12 tiles. Each consecutive row has 2 times the number of tiles as the row before. Write a function representing the number of tiles t in a specific row n. So we are talking about the number of tiles, and this first row here has 12 tiles. So we know that n equals 12 when t equals 12. My apologies. Let's clear that real quick. First row has 12 tiles. We know that t equals 12 when n equals 1. And this is a big difference between some of our previous problems. Usually, we're going to start when that n equals 0, and we're going to kind of see what adjustment we need to make in a second. So each consecutive row has 2 times the number of tiles, so we're going to multiply by 2 every single row that we go up. So if we write a function representing the number of tiles t as a input of the rows, let's start it with, okay, we're starting with 12. We are multiplying by 2 over and over again. And let's say we raise it to the n power for the number of rows. Now, if I were to look at this, though, and check it back against that first piece of information that I wrote down, t equals 12 when n equals 1. We look at it and we see, all right, let's say we plugged in n of 1, we'd have 12 times 2 to the first power. That means we would get 24. That's really not what's happening here. What we want is we want 12 times 2 to the 0 power, which would get us back down to 12, right? Because the 0 power is 1. So really what we have to do is we need to, in our exponent, subtract 1 to make sure that that initial term lines up with 1. Usually our initial terms kind of lined it up with 0, so it worked out okay. Let's kind of graph these two things real quick to show you what I'm talking about. So we get some t of n, and that equals 12 times 2 to the n power. And this is the incorrect version that I was talking about. And it looks like if I go here and I look at what's happening, at a input of 0, I have the number of tiles of 12. And contextually in our problem, can we have like a 0th row of tiles? No, it always starts at the first row. So this doesn't make sense with the context of our problem. But if we shift this over and go, all right, -1 like we talked about, and we'll need to use some parentheses around there. Okay, we'll notice that that value for 12 shifted over, and it is now happening when there is an input of 1 tile. So that, or sorry, 1 row. So that first row tile now lines up with what we wanted at 12 tiles, and our function is good. So with this then, if we wanted to calculate how many tiles were in the 5th row, we go t of 5 equals 12 times 2, and we plug in 5 minus 1. I'm going to throw that in parentheses. If you have this graphed, you could just go in and type in t of 5 if you wanted, and get an answer. I'm going to throw it in and actually evaluate it just in case. Go 5 minus 1 up top. And it looks like I got the same thing for both, which makes sense. I have 192 tiles in that 5th row.